So if you ever spill a toner cartridge inside a laser printer, your very first instinct is probably to grab the nearest vacuum to suck up the mess.
Right. I mean, that makes total sense.
Yeah, but if you use a standard household vacuum to do it, you won't just ruin the vacuum.
Oh, absolutely not. It's much worse.
You will likely generate this, massive jolt of static electricity that instantly fries the printer's motherboard.
Yep. Completely catastrophic.
Welcome to the deep dive. Today, we are looking at the hidden, honestly, highly volatile engineering inside those beige machines sitting quietly on your desk.
We really do tend to view printing as just, simple digital file transfer. You hit a button, a page comes out.
Exactly.
But if you're pulling from the CompTIA A+ IT certification training materials, specifically Professor Messer's course notes on hardware, you quickly realize these devices are actually complex industrial manufacturing plants, just scaled down to fit next to your monitor.
And our mission today is to decode the four major categories outlined in those sources. So we've got impact, inkjet, laser, and thermal. Because understanding the physics and the chemistry and the electrical engineering behind these, it isn't just about passing an IT exam.
No, not at all.
It transforms you from someone who simply, hopes for the best when hitting print into someone who knows exactly how to troubleshoot the machinery.
It gives you that mechanical intuition.
Okay, let's unpack this. I want to start with the evolution of physical precision. Let's wind the clock back to the most brute force mechanical method on the list, the dot matrix printer.
Yeah, so we are starting at the absolute foundation of the technology here, which is physical impact.
Right.
A dot matrix printer creates an image using a tightly packed column of tiny metal pins. And these pins fire outward, physically striking a fabric ribbon that's soaked in ink and basically smashing that ink into the paper.
Smashing is definitely the right word.
It really is. And we're talking about pins firing and retracting hundreds of times per second.
Which requires a massive amount of kinetic energy.
Oh, huge.
Because moving a metal pin that fast over and over, it's going to generate extreme friction and heat.
Exactly.
And that explains why the back of a dot matrix print head is essentially one giant metal heat sink.
Yeah, it has to be.
It has to dissipate all that thermal energy so the pins don't literally fuse together inside the housing.
Right, and that kinetic energy, that is the whole point of the machine. It's a loud, aggressive process.
Very loud. Like a tiny, aggressive, automated typewriter.
Perfectly said.
Yeah.
You wouldn't want it running in a quiet office environment. And, the resolution is incredibly low compared to modern standards.
Yeah, so why does anyone still use them?
Well, that specific physical strike solves a logistics problem that liquid ink or dry powder simply cannot touch, and that is multi-part forms.
Ah, right, because a laser printer just gently rests plastic powder on the surface of the page.
Exactly. There's zero physical force.
So if you are, say, a car dealership or a warehouse and you need a customer signature to instantly transfer through 3 layers of paper for invoices, you needed the brute force of those pins pushing down.
You need that impact. And it's funny, the term carbon copy is actually a bit of an anachronism now.
Wait, really?
Yeah. The Professor Messer materials highlight that modern multi-part forms rely on a fascinating bit of invisible chemistry rather than, sheets of messy black carbon paper.
Oh, I was looking at that. The chemistry of copies. It's wild.
It really is.
So the back of the top sheet is coated with a microscopic layer of encapsulated ink, right?
Yeah.
And then the front of the second sheet is coated in a reactive clay.
Exactly.
So the printer doesn't even use its own ink for the copies beneath the top page.
Nope. The impact of the pins actually crushes those microcapsules on the back of the first sheet.
Wow.
And that releases the chemical onto the clay of the second sheet to instantly form the black text.
That is just brilliantly efficient.
It is. However, there is a catch. Frequent handling of that specific combination of chemical dyes and reactive clay is known to cause skin irritation.
Oh, right.
So that's a primary reason why many IT departments are trying to phase them out in favor of simply printing multiple single pages on much faster machines.
That makes sense. But where they are still used, the IT maintenance is entirely focused on mechanical realities, right?
Pretty much exclusively.
Because maintenance seems surprisingly straightforward. Like when the print starts looking faded, you don't pour liquid in?
No, you just swap out the ribbon cartridge.
Right. And it's usually a toolless process. You pop out a plastic loop, snap a new one in, and you are back up and running.
It takes seconds.
But the paper path, that seems a lot more unforgiving.
Oh, yeah, you're referring to the tractor feed system.
Yes.
Dot matrix printers, They don't use standard stacks of cut A4 paper. They use continuous fan-folded paper with a strip of perforations and holes running down both sides.
Sometimes it's that classic alternating green bar paper, right?
Yeah, the stuff historically used to review thousands of lines of source code.
The precision required just to load that paper is honestly stressful.
It really is.
Because those holes have to perfectly align with the sprockets on the tractor feed gears. If you are off by even a millimeter, the paper will eventually torque itself sideways as it feeds, creating a catastrophic accordion-style jam.
And the machine doesn't know it's jammed. It just keeps firing pins into a crumpled mess.
It's a nightmare.
It demands perfection from the user just to set it up. So we have this aggressive, noisy, mechanically complex system.
Right.
And the natural engineering progression from there was to figure out how to maintain the image quality while completely eliminating the violent physical strike.
Which brings us to fluid dynamics.
Yes.
The inkjet printer trades metal pins for microscopic liquid dispersion.
It's a huge leap.
We go from a machine that sounds like a tiny jackhammer to one that operates in near silence, offering incredibly high resolution and color blending.
The engineering shift here is profound. Instead of hitting a ribbon, the print head hovers over the paper and ejects microscopic droplets of liquid ink.
Just spraying it.
Right.
Yeah.
And to get the precision needed for a high-resolution photograph, those droplets have to be perfectly timed and placed.
I can imagine.
And to do that, manufacturers use different ejection methods, like piezoelectric crystals that physically change shape when an electric current is applied.
Wow.
Or tiny thermal resistors that literally boil the ink to create a vapor bubble that forces a droplet out of the nozzle.
Wait. Boiling microscopic drops of cyan, magenta, yellow, and black ink.
Yep, the CMYK model.
That explains the exceptional color blending. But introducing liquid exposed to the open air introduces a completely new IT nightmare.
Oh, absolutely. The clog.
The absolute bane of my existence.
It is the defining vulnerability of the inkjet printer. I mean, the ink is proprietary, it's expensive, and it is fundamentally designed to dry quickly once it hits the paper.
Right.
The problem is it also dries quickly when it's just sitting in the microscopic nozzles of the print head.
So if you print a test page and see horizontal white streaks cutting through your text or your images, that's the telltale sign, right?
Exactly. Dried ink has created a physical blockage in specific nozzles.
So how do the machines deal with that?
Well, to mitigate that, inkjet printers are programmed to run automated maintenance cycles. If you leave the printer plugged in, you'll often hear it spinning up in the middle of the night.
Oh, I've always wondered why it does that.
Yeah, it is physically moving the print head over a small wiper blade and purging a tiny amount of fresh ink to dissolve any drying clogs.
Okay, that makes sense.
And you can manually trigger these deep cleaning cycles from the computer if the streaking gets really bad.
But if the clog is too stubborn, you have to replace the print head.
Yes.
But hold on, I have a pushback question here. If the print head is so fragile and prone to clogging, why do I usually just buy those cheap little plastic ink tanks at the store? I mean, I've never had to replace a shiny metal plate.
So that is a deliberate architectural choice by the manufacturer regarding the printhead.
Okay.
The actual printhead mechanism, while microscopic and incredibly precise, it can be manufactured relatively cheaply.
Really?
Yeah. So some brands integrate the ink reservoir and the printhead into one modular unit.
Oh, I see.
Which means every time you run out of ink and swap the cartridge, you are simultaneously installing a brand new factory clean printhead.
It's basically a brute force way to solve the clogging problem. Just throw the entire mechanism away.
It is. And it obviously drives up the cost of the consumable significantly.
Right.
The alternative, which it sounds like you've experienced, is a printer with a permanent heavy-duty printhead built into the chassis.
Yeah.
You only buy the cheaper liquid ink tanks, but you assume the risk of maintaining that permanent printhead. If it clogs beyond repair, the entire printer is often a total loss.
That is quite the gamble. And regardless of the system, whenever you insert a new set of cartridges, you have to run that calibration page.
Oh, yeah.
The printer spits out a sheet covered in slightly overlapping grids and numbered lines, and you have to tell the computer which lines look the sharpest.
Yep.
You are literally helping the printer's microscopic timing align so the cyan and magenta droplets land on the exact same micron of paper.
It's an incredible level of high-tech liquid manipulation. But there is a really fascinating paradox here.
Okay.
For all of this sub-millimeter piezoelectric wizardry, the actual mechanism moving the paper through the machine is remarkably primitive.
Here's where it gets really interesting.
Yeah.
It's just rubber friction rollers.
Literally just rubber wheels.
It's just a little rubber wheel grabbing the top sheet of paper and pulling it in. It's a great reminder that high-tech always rests on low-tech.
Always.
Because as that rubber wheel ages, it picks up paper dust and environmental grime, and it gets slick.
Yeah, it loses its grip.
So when your printer makes that awful grinding noise and the paper just sits there in the tray, it's rarely a complex mechanical failure.
Almost never.
The roller just lost its friction. You wipe it down with a damp cloth, restore the grip, and it works perfectly again.
It's that simple.
Oh, and as a quick aside for you listening, the IT materials strongly advise recycling those empty plastic cartridges. They are massive contributors to e-waste.
Very good practice.
Okay, so we've covered the mechanical force of dot matrix and the fluid dynamics of inkjet.
Right.
The next evolutionary step in printing abandons physical force in liquid entirely. We move into the realm of subatomic electrical manipulation,
My favorite.
the laser printer. This completely reframes what a printer is.
It really does.
We are moving from a device that passes a single print head back and forth to an electrostatic machine that processes and builds the entire page simultaneously.
It operates much more like a miniature printing press, just powered by static electricity.
The processing power required for this must be immense.
It is, because unlike an inkjet that just receives a stream of line-by-line instructions, a laser printer has its own dedicated CPU and memory.
Wow.
It must fully render the complex geometry of the entire page in its onboard memory before a single physical action even occurs.
Walk us through that electrostatic choreography, because the engineering here is staggering.
It really is.
It all centers around a photosensitive cylinder, right?
Sure.
The OPC drum, the organic photoconductor.
Yes. The OPC drum is the absolute heart of the system. The process begins with a component called a corona wire, or in newer models, a primary charge roller.
Okay.
And this component ionizes the air to apply a massive, uniform negative electrical charge across the entire surface of the spinning OPC drum,
How massive are we talking?
typically around negative 600 volts.
So the drum is just a spinning cylinder of negative energy.
Exactly. Then, the laser fires, but it doesn't move like a scanner.
What does it do?
A stationary laser beams into a rapidly spinning polygonal mirror, which bounces the light across the surface of the drum.
And here is the crucial inverse logic of a laser printer. The laser doesn't add the image to the drum.
No, it doesn't.
Where the laser's light strikes the photosensitive surface, it actually discharges the negative energy, neutralizing those specific microscopic spots.
Precisely. It drops the voltage from negative 600 down to roughly negative 100 volts.
It is drawing with neutrality.
Yeah, that's a great way to put it. You are left with a heavily negative drum carrying an invisible, neutralized silhouette of your document.
It's incredible.
Next, we introduce the toner.
Now, toner is wild because it looks like black liquid in a bottle, but it is actually a microscopic, completely dry plastic powder mixed with iron particles.
Yep, dry plastic dust. And the printer applies a negative electrical charge to that plastic powder.
Like repels like.
Exactly.
So when that negative plastic powder is brought near the drum, it is violently pushed away from the negative 600-volt background.
Right.
But it is instantly attracted to the neutralized negative 100-volt spots where the laser hit.
It's essentially clinging to the drum through static attraction.
The image is now physically manifested on the drum in plastic dust.
Yes. And from there, the paper is pulled into the machine and passed under a transfer roller.
Okay.
This roller applies a strong positive charge to the back of the paper.
Opposites attract. The positive paper rips the negative toner dust right off the drum.
Exactly. But if you pulled the paper out of the printer at that exact moment, a slight breeze would ruin the whole document.
Oh, because the plastic dust is just sitting there.
Right. Held only by static. There has to be a way to lock it in.
That is the job of the fuser assembly.
Yes.
The paper is fed between two rollers in the fuser. Inside one of those rollers is a powerful high-tech heating element, often like a halogen lamp.
Basically an industrial oven.
The fuser acts like a laminator, but instead of melting a plastic sheet over the paper, it uses intense heat and physical pressure to melt the microscopic plastic dust directly into the fibers of the paper.
And that completely explains why laser-printed pages always feel warm when you grab them out of the output tray.
It feels great in the winter.
It does. The plastic has literally just been baked into the page.
It is a miniature oven, and because this process involves extreme heat, high voltage static electricity, and a multitude of precisely timed gears, Laser printers require rigorous preventative maintenance.
You definitely don't just wait for it to break.
The CompTIA materials heavily emphasize internal page counters. IT departments buy maintenance kits, which contain a new fuser, new pickup rollers, and new transfer rollers. And they install them the moment the internal page counter hits a specific threshold, say 100,000 pages, whether the printer is acting up or not.
It's all about preventing catastrophic failures. But maintaining a laser printer introduces serious safety hazards that IT professionals are tested on.
Yeah, let's talk about those.
First is the thermal hazard. If a printer was just used, the fuser is hot enough to cause severe burns. You absolutely must give it time to cool down before opening that assembly.
And the second hazard is the toner itself. We mentioned this in the intro, but it definitely bears repeating.
Please do.
Because toner is an incredibly fine, statically charged plastic dust, you have to be extremely careful if a cartridge spills inside the chassis.
Extremely careful.
The absolute worst thing you can do is hit it with a can of compressed air.
Oh, terrible idea.
You will instantly create an airborne, toxic cloud of plastic particulate that coats your lungs and the entire room.
You have to vacuum it. But as we noted, using a standard household vacuum creates a localized static storm.
You're right, because of the friction.
Exactly. The friction of the dry dust moving through a plastic hose generates massive static buildup. Since static electricity is the enemy of microelectronics, you will discharge that static into the printer's motherboard and permanently fry it.
So what do you use?
IT professionals use specialized grounded toner vacuums designed specifically to safely transport statically charged dust.
And here's another thing. If you get that plastic toner dust on your hands while changing a cartridge, your instinct is probably to go to the sink and scrub with hot, soapy water.
Which is another mistake.
Big mistake. Think about the physics we just discussed. Heat melts toner.
Right.
If you use hot water on your hands, you will literally melt the plastic dust directly into the pores of your skin, making it almost impossible to wash off. Always, always use cold water.
It's just a perfect example of how understanding the underlying engineering informs the daily maintenance.
Absolutely.
So we've gone from mechanical ribbons to liquid sprays to melting plastic powder with lasers.
What's next?
The final category abandons ink and toner entirely. We move into molecular chemistry.
The thermal printer. After the dizzying complexity of the laser printer, the thermal printer almost feels like magic.
Really good.
It uses absolutely no ink, no ribbon, and no toner cartridges. Nothing is physically applied to the paper.
Thermal printing is the technology behind store receipts, barcode labels, and the shipping labels on your packages.
Right.
And the mechanism is shockingly simple. There is a stationary heating element, often a solid-state ceramic bar, that spans the entire width of the paper path.
So it doesn't sweep back and forth like an inkjet?
Nope, it's completely stationary. A simple friction roller just continuously pulls the paper over this stationary bar.
The secret is entirely contained within the paper itself.
Exactly.
Thermal printers require thermochromic paper. The paper is manufactured with a specialized chemical coating that reacts to heat.
Yeah.
The stationary print head just selectively heats up microscopic dots along the bar. And as the paper slides over it, that heat triggers a localized chemical reaction that turns the coating black.
It's elegant. And because there are so few moving parts, basically just a roller and paper, it is nearly silent and highly reliable.
Right, there are no consumable cartridges to swap out.
None. The primary maintenance task is just occasionally wiping down that stationary heating element with a swab of isopropyl alcohol.
Or running a specialized cleaning card through the paper feed to remove environmental dust.
Exactly.
So, what does this all mean? It's arguably the lowest maintenance machine on the IT network. But the irony of the thermal printer is that while the hardware is incredibly robust, the output it produces is the most fragile.
That is the inherent trade-off. The paper is fundamentally designed to react to heat. The printer doesn't lock that chemical state, it just triggers it.
Which means any environmental heat will continue to trigger it.
Right. If you leave a thermal printed receipt on your car dashboard on a sunny summer day or set it near a heating vent, the ambient temperature will cause the entire page to turn jet black.
The data is completely destroyed.
Gone.
The sources highlight a chemical vulnerability, too. If you run a warehouse and print a thermal shipping label, you might be tempted to put a strip of clear packing tape over the barcode to protect it from the rain.
Seems logical.
But the adhesive in standard clear tape causes a chemical reaction with the thermochromic coating. It turns the printed area white, completely erasing the barcode underneath the tape.
It is highly reactive paper. And even under perfect temperature-controlled conditions, the chemical state naturally degrades.
It just fades.
Yep, the contrast fades over time. A thermal receipt kept in a file cabinet will often revert to a blank white strip of paper within a year or two.
Which dictates IT policy. If your accounting department relies on thermal receipts for tax records, those physical receipts are basically useless for long-term archiving.
Completely useless.
They must be immediately photocopied or digitally scanned before the chemistry fails. The extreme simplicity of the hardware requires hypervigilance regarding the output.
Precisely. And I think that brings us full circle. By looking at these 4 technologies, we see a really fascinating evolution of problem solving.
We went from the loud, brute force kinetic energy of the dot matrix relying on physical impact to the microscopic fluid dynamics and piezoelectric ejections of the inkjet,
Yep.
to the high voltage electrostatic choreography of the laser printer melting plastic, and finally to the solid state heat activated molecular chemistry of the thermal printer.
When you sit for an IT certification, you learn pretty quickly that a printer problem is never just a random glitch.
No.
It is a highly specific failure of a mechanical, chemical, or electrical process.
Exactly.
Troubleshooting a clogged liquid nozzle requires a completely different mindset than diagnosing a degraded, high-voltage corona wire.
But beyond the IT troubleshooting, Professor Messer's sources leave us with a really provocative thought about the permanence of our physical world.
Oh, for sure.
Think about the information you print out.
Every printing method we explore dictates a drastically different lifespan for the information it records.
Thermal receipts literally vanish into thin air from the heat of a sunny room. Inkjet photographs are stunning today, but the liquid dyes will slowly fade as ultraviolet light breaks them down over the years.
But a laser-printed document?
Right, where plastic is permanently baked into the paper fibers, that could conceivably outlast us all.
It makes you wonder, how much of our recorded history, how much of what survives for the next generation to actually hold and read, is being quietly determined by the specific engineering of the machine you chose to hit print on today?
It's a wild thought.
The next time someone hands you a document, look closely. See if you can spot the tiny dots of impact, the smooth color blending of liquid drops, or the melted plastic sheen of toner.
It changes how you see them.
Once you understand the physics on the page,
Yeah.
you will never look at that beige box on your desk the same way again. Thanks for taking this deep dive with us.